So far in this unit, we've been talking about the behavior of how things fly through the air when they're launched horizontally, and then they're only under the influence of the force of gravity. So when we looked at the force diagram, we said that gravity was the only significant force acting on them, and air resistance was insignificant. And we talked about the fact that because there's no significant forces in the x direction, the horizontal part of the motion as they fly through the air, the velocity is constant and there's zero acceleration. In the y direction, the only significant force is the force of gravity, and so the y part of the motion is going to have an acceleration of -10 meters per second per second. So we've already looked at a two-dimensional motion map of a horizontal projectile, in this case a mountain biker riding off the edge of a level cliff. The horizontal part of the motion stays constant at 20 meters per second, and as they fall through the air, velocity in the y direction is getting more negative. So after a second, it'd be -10 meters per second. After 2 seconds, it would be -20 meters per second. And after 3 seconds, the vertical part of the velocity would be -30 meters per second. In this video, we're going to try to think about how to deal with situations where the initial launch velocity is not just horizontal, where it's angled upward or the initial velocity is angled downward. So remember, when we talked about our mountain biker or something, let's say rolling off of a level cliff, all of the velocity is horizontal, none of it is vertical yet until they leave the edge of the cliff. So how do we think about a situation where a biker is launched upwards at an angle or downwards at an angle? Well, in the case of upwards at an angle, that initial velocity is both the left and up. And so just like we did with forces, when we had a force at an angle, we broke it up into its horizontal and vertical components. We'll do the same thing with its velocity. So if the initial velocity is at an angle of 20 degrees or some positive angle, it's got a x component to its velocity, initial velocity, and a y component to its initial velocity. So what effect does that have on how much time it spends in the air? Well, if we go back to our horizontally launched velocity, remember that vertically it behaves just like a dropped object because its initial velocity was 0 in the y direction, and then it's going to accelerate at -10 meters per second per second. Well, what's true of the vertical part of the biker's motion that has an upward angle launch? Well, it's got a positive y velocity, so that's going to behave like, let's say, tossing a ball straight up. It's got to slow down on its way up and then speed up on its way down, and so it's going to spend more time in the air. And so if we look at this angled launch, the time increases, and so it's going to have more time to travel out horizontally. In the situation of the downward angle launch, again, we're going to split up its initial velocity into its x component and y component. And if this thing is launched downward, then the y component will be negative, and that has implications for how much time it's going to spend in the air. If you think about it, if we're thinking about just the vertical part of the motion, if you have a negative initial y velocity, it's like you've thrown something downward versus just letting it drop. And if you throw something downward, it's going to take less time to hit the ground below or have its vertical displacement. And so if we're talking about the path that it follows and the amount of time that it spends in the air, it's going to follow a path something like this. And it's going to take less time to hit the ground because it's already moving down vertically once it leaves the edge of the cliff. So let's focus on the situation where we have an upward angle launch, and just like we did with horizontal projectiles, let's make a two-dimensional motion map. So this is the parabolic type path that the biker will follow, and on a motion map we have dots which represent the position of the object during equal intervals of time. And so it's going to look something like this. It's going to travel horizontally some distance and it's going to move up. The next dot is going to be the same horizontal displacement over because the x part of the velocity doesn't change. There's no significant forces in the x direction, so there's going to be equal spacing horizontally. But vertically, it's slowing down as it rises, and so it's not going to travel up as far. When we add our horizontal components to the velocity, it looks something like this. We know that the horizontal part of the velocity stays the same at every individual position. What about the vertical component of the velocity? Well, it initially has some vertical velocity, but as it rises, the vertical component has to get smaller. And if we're at its maximum height, the vertical component of the velocity is 0. gravity slows it down to rest just at that instant at the very top of its flight. 1 instant later, it's going to be falling downward with a small negative vertical velocity. The next instant, it'll be a larger negative velocity, and by the time it hits the ground, it'll have the largest negative velocity. Well, remember, the blue arrows represent the horizontal component of the velocity, and the red arrows represent the vertical component of the velocity, but those are pieces of the actual velocity. The purple arrow here reminds us that this is the actual speed and direction at the moment of launch, and if we want to figure out how big the velocity is and in what direction, we're going to use the horizontal and vertical components, and if we put those things together to make, let's say, the hypotenuse of our right triangle, this represents the actual velocity at the second instant in time. At the very top, there is no vertical component of the velocity, and so the actual velocity will be equal to the x component of the velocity. The next instant in time, it's going to be angled left and downward. The next instant in time, it's going to be left and more downward, so it's going to be more angled down towards the ground, and so on like this. So this is what a qualitative two-dimensional motion map looks like for something that's launched at an angle. Now, there's a special case that I want to talk about before we move on and try to solve this kind of a problem quantitatively. It has to do with when the projectile or the object reaches the same height it was launched from. So this dot right here is at the same vertical position as its initial vertical position. And if we look at the components of the velocity, we know the horizontal component has to be the same as the initial horizontal component of the velocity. But what's true of the vertical component of the velocity when it reaches the same height? So remember, think about the vertical part of the velocity just like either a dropped object or an object, in this case, thrown upward. And so if you were to throw, let's say, a tennis ball up at 5 meters per second, positive 5 meters per second, it's going to go up, gravity's going to slow it down, and then gravity's going to speed it up. By the time it makes it back down to your hand, if you throw it up at 5 meters per second, it's going to be moving at 5 meters per second in the negative direction when it makes it back down to your hand. Or if you throw it up at 20 meters per second, it's going to go higher, and then gravity's going to accelerate it back down, and it's going to be going at 20 meters per second just in the negative direction. So if the initial y component of the velocity is, let's say, this big at the beginning, by the time it makes it back to the same height, the vertical component of the velocity will be the exact same size as what it was in the beginning, just in the opposite direction. And this is going to actually allow us to solve some problems much easier if we know this fact or remember this fact. So let's say our mountain biker is launched from a 3-meter tall cliff at an angle of 20 degrees like this, and let's say the biker is initially moving at 10 meters per second. Let's figure out two things. How much time do they spend in the air, and how far do they travel horizontally, or what's their horizontal displacement? Well, just like we solved our horizontal projectile problems, there's lots of potential given information or information that we need to write down before we start thinking about equations. Well, part of that involves the horizontal velocity in the x direction and the initial vertical velocity, or velocity in the y direction. And so just like we did with forces, if we have, in this case, a velocity, which is the hypotenuse, and we know what the angle is, we can solve for the length of the adjacent side, which is the horizontal component of the velocity, and the vertical or opposite side of the triangle, which is the y component of the velocity. So when we solve for the x component of the velocity initially, it turns out to be the hypotenuse, which is 10 meters per second, times the cosine of 20 degrees, which turns out to be 9.39 meters per second, and we make that negative because the initial horizontal component is to the left. For the vertical component of the initial velocity, that's the hypotenuse times the sine of 20 degrees, and that's 3.42 meters per second, and we make that positive because, as we can see, the initial vertical component is up, and up is positive. So let's write down now our given information. The initial component of the velocity in the x direction was negative 9.39 meters per second. there is no acceleration in the x direction, so the final velocity in the x direction is also negative 9.39 meters per second. We calculated the initial velocity in the y direction was positive 3.42 meters per second, and we don't know how fast it's moving vertically by the time it makes it all the way down to the ground. But we do know the acceleration in the y direction is negative 10 meters per second each second. And if it starts from a height of 3 meters and goes down to a height of 0 meters, the change in y position, or vertical displacement, is negative 3 meters. So let's first solve for the time that the biker spends in the air, and then figure out how far they travel horizontally. Well, when we did this for horizontal projectile problems, we solved for time using information about the vertical part of the motion, or the y direction. So let's do the same thing, except this time we're going to have to use a slightly different equation. If we use our kinematic equation, which is final velocity in the y squared is equal to the initial velocity squared plus 2 times the acceleration in the y direction times the change in y position, we can solve for the final velocity in the y direction and then use that to figure out what the time is. So we get Vy squared is equal to the initial velocity, which is positive 3.42 meters per second squared, plus 2 times the acceleration in the y direction, negative 10 meters per second, times the change in y position, which is negative 3 meters. When we solve this equation algebraically for the final velocity in the y direction, we find that it's negative 8.47 meters per second. Now, since we know that, we can now use that final velocity in the y direction to solve for time. So let's use another one of our kinematic equations, which is final velocity is equal to initial velocity plus acceleration times time. All this information again has to be from the y part of the motion. So we just found out that the final velocity is negative 8.47 meters per second, which is equal to the initial velocity, positive 3.42 meters per second, plus our acceleration, negative 10 meters per second, multiplied by time. When we solve this equation for time, we find out that the time that it spends in the air vertically is about 1.19 meters per second. Well, if it spends that much time moving in the vertical direction, it's going to spend that same amount of time moving in the horizontal direction. And so if we want to solve for the horizontal displacement, let's now look to our information about the horizontal part of the motion. So let's use our displacement equation. Change in x is equal to initial velocity in the x direction times time plus 1/2 times the acceleration in the x direction multiplied by time squared. This whole last term goes to 0 because, as we've written down here, there is no acceleration in the x direction. And so 1/2 at squared all goes to 0. And so we take our initial velocity in the x direction, which is negative 9.39 meters per second, and multiply it by the time it's in the air, 1.19 seconds, and we get that the displacement is negative 11.17 meters. So the process is not that much different than we use for solving horizontal projectile problems, where the initial vertical component of the velocity was 0. The only difference is we have to add an extra step and use 2 equations in the vertical direction to solve for time, and then use that to figure out something like horizontal displacement. Now, the only other possible question I could ask you, or different type of question, would be, what if the mountain biker, instead of being launched upwards at an angle of 20 degrees, let's say they're launched downward at an angle of 20 degrees. And it turns out how we solve it and the answer is actually not much different. So let's just quickly look at that and see what changes. So if we look at our situation here, let's say they're launched same speed at 10 meters per second. Instead of at an upwards angle, they're now 20 degrees below the horizontal. They're still going to have a horizontal component of the velocity, but now a negative component to the y velocity. And so the things that change are highlighted from our last situation. The vertical component is still 3.42 meters per second in size, but it's negative. And so that'll change the given information up here. So when we're solving for time, well, we're first going to find the final velocity in the y direction. And if we plug in negative 3.42 meters per second for the initial velocity in the y direction, turns out it doesn't actually change how fast the mountain biker is moving when they hit the ground. But it will change our time, because we have our final velocity is equal to the initial velocity, which is now negative 3.42 meters per second, plus acceleration times time. And because of that sign change right there, turns out that instead of 1.19 seconds, turns out the time is 0.51 seconds. So it spends much less time in the air because initially it's already moving in the negative direction, and so it takes less time to hit the ground, to be displaced at -3 meters. And so if the mountain biker horizontally is moving at -9.39 meters per second for only 0.51 seconds, they're only going to be displaced horizontally -4.79 meters. I hope this helps you think about projectiles that are launched either at an upwards angle or at a downwards angle, and you'll have more time to practice this in your homework.